Hello everyone and welcome back to our lecture series. Before we explore today's topic, let's take a moment to recap the key points from our previous video. In our last session, we learned about the basic concepts of infinite sequences and discussed the definition of convergence and divergence for sequences. If you missed that lecture, no worries, you can find it in the playlist linked below. Now, based on that knowledge, let's talk about today's discussion on different theorems that we can use to calculate the limits of convergent sequences. So let's get started. Alright, the first theorem provides a systematic way to find the limits of sequences through the basic arithmetic operations. If a sub n and b sub n are convergent sequences with the limits a and b respectively, based on the sum rule, then the sum sequence a sub n plus b sub n is also convergent, and the limit of the sum sequence is the sum of the limits of the individual sequences. Also, as I write here, we can also apply similar rules to subtraction, multiplication, and division of two sequences. For example, the quotient rule indicates that the ratio of two convergent sequences, as long as the denominator sequence does not converge to 0, will result in a convergent sequence. The limit of the quotient sequence is obtained by dividing the limit of the numerator sequence by the limits of the denominator sequence. Okay, let's reinforce our understanding with a few examples. For calculating the limit of minus 7 over n squared, we can use the constant multiple rule and product rule. Additionally, as discussed in the last video, the limit of 1 over n as n approaches infinity is 0. Therefore, both these two terms in the expression tend towards 0. So the final answer is equals 0. As another example, let's find the limit of the 7n plus 5 over n. By decomposing the fraction into its parts, we can use the sum rule and express the limit as the sum of 7 plus 5 over n. The answer of the first part is 7, as it's a constant number. For calculating the limit of 5 over n, we can use the constant multiple rule, so the final answer would be 7. Now let's talk a little bit about sandwich theorem, which is also known as the Squeeze Theorem in mathematics. Consider a sandwich with two slices of bread and meat between them. Similarly, in mathematics, we have an upper sequence, a lower sequence, and a middle sequence. Imagine someone biting into the sandwich. The upper and lower bread come closer and the inner meat follows through it. In the same way, in mathematics, if both the upper and lower sequences have the limit of L, the middle sequence also converge to L. An immediate consequence of this expression is that if we substitute the a sub n with minus c sub n, we can rewrite the inequality expression like this. Now, both if the upper and the lower sequences have limits approaching 0, based on sandwich theorem, it leads to the conclusion that the limit of the middle sequence or b sub n is also 0. This theorem is a valuable tool for calculating the limits of complex or challenging function in mathematics. Since we have learned about the concept of the sandwich theorem, we can now use it to calculate the limits of sine n over n and cosine n over n. If we plot both sine and cosine on the Cartesian plane, it is evident that both of them have a range between -1 and 1. In other words, as the value of n varies, the sine and cosine function oscillate between -1 and 1. So based on this fact, if we divide both sides of these two expressions by n, the new range would be from -1 over n to 1 over n. As n approaches infinity, both sides of these two expressions converge to 0. Consequently, the limit for the both middle sequences would also be 0. Here we see the third theorem for calculating the limits of sequences. This rule, which is called the continuous function theorem, states that if a sequence a sub n converges to L, then for any continuous function, the f of a sub n sequence also converges to f of L. Simply, we can also learn and apply this theorem by just memorizing these sentences, that the limit always passes through a continuous function. So for finding the limits of any example by this rule, we just make sure that the function is continuous. Then we can let the limit passes through function. For example, we know that the sine function is a continuous over its entire domain. So we are allowed to let the limit passes through this function. So if the limit passes through this function, then we know that the limit for pi halves plus 1 over n is pi halves, and the sine of pi halves is 1. The fourth and the last rule for calculating the limit for sequences is L'Hôpital's rule. The rule states that if the limit of the ratio of two sequences as n approaches infinity is an indeterminate form like infinity over infinity or 0 over 0, then we can take the derivative of both the numerator and the denominator. And the limit of the ratio is equal to the limit of the ratio of their derivatives. As an example, as n approaches infinity, both the numerator and the denominator become infinity. Consequently, the result is an indeterminate form. By applying the L'Hôpital's rules twice, the answer would be 0.